So here we have a Calculus 3C problem where it asks us to evaluate the integral by making an appropriate change of variables. We have the double integral in the region of R, 5 times x plus y times e to the x squared minus y squared, where R is the rectangle enclosed by the lines x minus y equals 0, x minus y equals 6, x plus y equals 0, and x plus y equals 5. Now I'd like to note that we have an x plus a y here, and that x squared minus y squared equals x plus y times x minus y. And that will be important when we're trying to figure out what u and v equal when we complete the transformation. Now what I like to do when I start this type of problem is to graph it, just to make sure that we actually need to transform the variables to make it easier to integrate. And you can see that we've solved these boundary equations for y and graphed it on this little brown graph down here with x and y coordinates. And you can see that with this purple these purple lines here, that you would have to do 3 different integrals in order to integrate it, which is why we want to transform it. So to start the transformation, we can see that we have 2 different types of functions with x minus y equaling something and x plus y equaling something. So logically we would think that we would have u equal x plus y and v equal x minus y. And then we can start doing the transformation to change the boundaries, so we can have u equal x plus y equal 0, and u equal x plus y, which equals 6. V equal minus y. And then we have v equal x plus y, which equals 0, and v equal x plus y, which equals 5. Let me fix this up here. And then we have the boundaries of u being between 0 and 6, and v being between 0 and 5. And now we can use these equations up here to solve for x and y using a system of equations, and then we can find the Jacobian for that to complete the transformation. So if we add these two together, we get u plus v equals 2x. And if we divide by 2, we get u plus 1/2 u plus v equals x. And that will be our x function. And then if we multiply the u function by -1, we get negative u equals negative x plus y. And if we add the v function to it, we'll get v minus u equals 2y. And then if you divide by 2, you get 1/2 v minus u equals y. And that's your second function that we'll use to make this Jacobian, which is the derivative of xy over the derivative of uv. And we have to make sure that the Jacobian is always the absolute value. So even if we get a negative answer here, we're going to plug in the positive value into our integral. And so this will be dx over du, dx over dv, dy over du, dy over dv, which equals, so over here if we take the derivative with respect to of x with respect to u, we get 1/2 because the v is considered a variable. So we have 1/2 for the derivative with respect to u. With the derivative with respect to v, we also get 1/2 with x. And if we take the derivative of y with respect to u, notice that we're going to get a negative 1/2. And if we take the derivative of y with respect to v, we'll get a positive 1/2. So this equals, if we cross multiply, 1/4 plus 1/4, which equals 1/2. And this is our Jacobian value. Now, we can safely replace all of our, transform everything so we can get our original integral in terms of u and v. So here we can make this, have our new double integral with 5. And remember we have x plus y equals v. V times e. And remember when I said that x squared minus y squared is important to notice? Well, now we can see that x squared minus y squared equals VU. So we can just replace this value up here with VU. And it seems to me that it would be easier to integrate u first, because then we don't have to do partial integrals, so we'll do that. We'll have du dv. And don't forget our Jacobian, which we'll just put right over here as the 1/2. And our boundaries, u goes from 0 to 6, and v goes from 0 to 5. Now we can factor out the 5/2 to make it a little bit easier to see. And then we'll have v e to the vu du dv, which will equal, when we integrate with respect to u, we'll have 5/2 on the outside, the boundary of v from 0 to 5, v e to the vu, and we'll divide by v. And we'll evaluate this from 0 to 6, dv. If we continue this problem, we'll have 5/2 from 0 to 5. And if, notice here that the v's cancel, so all we have to do is put an e, 6 6b, minus e to the 0 dv. Let's move it up here, eraser. And we'll move this up here. And we have 5/2 from 0 to 5, e to the 6v minus 1 dv, which equals 5/2 times e to the 6v over 6 minus v, evaluated from 0 to 5, which equals 5/2 times e to the 6 times 5, or 6 minus 5, minus 5/2 e to the 6 times 0, or 6 minus 0. We can factor out a 5/2, so then all that's left in here is e to the 30th over 6 minus 5, and this has been factored out, so we just have a negative e to the 0 over 6, which actually equals negative 1/6. And then if we multiply this by 6 on each top and the bottom, we can get a common denominator. So then we have 5/2 times e to the 30th over 6 minus 36 minus 1/6. So we get a final answer. And we can factor out a 6 over here, so we'll have 5/12 times e to the 30th minus 31. This is our final answer.